Hi, today we introduce bipolar junction transistors. They are also called BJTs in a shortened version. We are still using Crops Basic Electronics as our prescribed book. Okay, the aim of this topic is for us to understand bipolar junction transistor basics, how are they constructed, the operation biasing, and their applications. A bipolar junction transistor is a device consisting of three layers of doped semiconductor materials which may be used to control the flow of current. So just like a diode, it's also a doped semiconductor material, but now it has three layers, not two as a diode. A bipolar junction transistor can amplify voltage, current, or power, and it can also be used as an electronic switch. The construction of a BJT. There are two types of transistors that may be constructed from semiconductor materials such as silicon or germanium. There's the NPN transistor and the PNP transistor. The NPN transistor is made up of two N-type semiconductor materials and one P-type. And the PNP is made up of two P-type semiconductor materials and one N-type. So it makes up three terminals. The first being the emitter, then you have a base, and you also have a collector. How are these three terminals differentiated? We have an emitter, base, and a collector. So on an NPN transistor, the emitter will be made up of the N-type semiconductor material. The base will be made up of a P-type semiconductor material, and the collector will be made of an N-type semiconductor material. Then on a PNP transistor, it's just the opposite of that. For NPNs and PNP transistors, the emitter is heavily doped. Its job is to emit or inject current carriers into the base. The base region is very thin, narrow, and lightly doped. The collector region is moderately doped and is the largest of all the three because it must dissipate more heat than the emitter or the base regions. This diagram shows a current flow in an NPN transistor biased to operate in the active region. When it's biased to operate in the active region, it means that the base emitter is reverse biased, and then the collector base region is reverse biased. So in this state, the reverse current components due to drift of thermally generated minority current carriers are not shown. So here what we see is that most of the current carriers injected into the base from the emitter flow out through the collector lead, while only a few carriers flow out through the base lead. Then here we have a PNP transistor, so it's the opposite of that, whereby holes are injected into the collector. Therefore, they are collected, the holes will be collected on the collector region, while only a few holes will be diffused through the base. Current carriers and junction potential. So on an NPN transistor, the majority current carriers are free electrons in the emitter and the collector, whereas the majority current carriers are holes in the base. Remember that NPN, so it means that on the N-type you have N-type semiconductor material. Therefore, the majority current carriers will be free electrons. Also on the collector. Then on the middle, which is your base, you have a P-type semiconductor material. Therefore, the majority current carriers will be holes. Then on a PNP transistor, the majority current carriers are holes in the emitter and the collector because they are both made up of the P-type semiconductor material. And the majority current carriers are free electrons in the base because your base is made up of the N-type semiconductor material. For silicon BJT, the barrier potential for both the emitter base EB and the collector base CB junctions equals approximately to 0.7 volts. What is the schematic symbol of an NPN transistor? So an NPN transistor, this is how it will look like. On the left, you have a collector on top, base in the middle, and emitter in the bottom. So when you look at this structure, it looks like two diodes that are connected back to back. So from the base to the emitter, you have a diode that is looking towards the emitter. And then between the base and the collector, you have another diode that is facing the collector. But for us to differentiate between the collector and the emitter, we only show the diode between the base and the emitter. Then on an NPN transistor, because we have NPN, so the diodes are connected facing the base. So you have between C and B, and then you also have between E and B. So the diode is facing inside towards the base. But to differentiate between collector and emitter, we only show the emitter diode. BJT construction in summary: the emitter is the one that is heavily doped. It emits or injects current carriers into the base. For an NPN transistor, the N-type emitter injects free electrons into the base. For PNP transistor, the P-type emitter injects holes into the base. Then number 2, the base is very thin and lightly doped. Most of the current carriers injected into the base cross over into the collector side and do not flow out of the base lead. Then number 3, we have a collector which is moderately doped. It is also the largest region within the transistor. Its function is to collect or attract current carriers injected into the base region. Proper transistor biasing. There are basically 3 possible ways to connect a BJT within an electronic circuit. 1, it's the common base configuration. Number 2, it's the common emitter configuration. And then number 3, it's the common collector configuration. So the first one has a voltage gain but no current gain. The number 2, the common emitter configuration has both current and voltage gain, and then the common collector has current gain but no voltage gain. So it depends on what you want to achieve on your circuit, then you will choose any of the 3. Okay, this diagram shows the common base configuration. So you have collector, emitter, and base. Notice that the base is connected common to both voltage sources. Then you have your emitter and the collector connected to the other terminals of your supply. Then there will be current that flows in this circuit, IE, IB, and IC. Here the emitter base junction must be forward biased while the collector base junction must be reverse biased. Notice that the base lead is common to both connections. It is a common base configuration because the base lead is common to both the input and the output sides of the circuit. The emitter base junction supply voltage is designated VEE, and while the collector base junction is designated VCC. Okay, this is another circuit that shows the common base configuration whereby you have an input AC voltage and on the output you have a load resistor that's connected to the collector. Transistor currents. Most of the emitter injected electrons pass through the base and into the collector for two reasons. Number 1, only a few holes are available for recombination in the base. Remember, the base is very thin and lightly doped. The positive collector base voltage attracts nearly all the free electrons in the p-type base over to the collector side before they can recombine with holes in the base. Only a small collector base voltage is needed to create an electric field strong enough to collect almost all the free electrons injected into the base region. Too large collector base voltage can exceed the breakdown voltage and destroy the transistor. Remember, the CB region, it's reverse biased, so you need to know how much it's the maximum reverse voltage that this transistor can handle before it reaches the breakdown voltage. Voltage polarities and current flow in transistors biased in the active mode. So here we have on the left we have an NPN transistor, and then on the right hand side we have a PNP transistor. We notice that because of the arrow, when the arrow is pointing out, it means that the PN is from P to N, so it shows us that it's an NPN transistor. And then on the right hand side, the arrow is pointing in, meaning that it's moving from P to N, so it's PNP. We only show the arrow for the emitter. Then we have three currents. IC on the left hand side plus IB will be equals to IE. Then on the right hand side we have IE, which is equals to IB plus IC as well. Okay, transistor currents IE is equals to IB plus IC. The emitter current is equal to the base current plus the collector current, or the collector current is equals to the emitter current minus the base current, or base current minus is equals to the emitter current minus the collector current. Example 1, a transistor has the following currents. IB is equals to 20 milliamperes and IC is equals to 4.98 amperes. Calculate the emitter current IE. So your answer here would be IE is equals to the base current plus the collector current. 20 milliamperes plus 4.98 amperes is equals to 5 amperes. Example 2, a transistor has the following currents. IE, which is your emitter current, is equals to 100 milliamperes. IB, base current, is equals to 1.96 milliamperes. So the value of IC, it would be equals to what? IC would be equals to the emitter current minus the base current. So it gives us 98.04 milliamperes. Example 3, a transistor has the following currents. IE equals to 50 milliamperes. IC equals to 49 milliamperes. Calculate IB. So IB will be emitter current minus collector current, giving us 1 milliamperes. DC alpha. DC alpha describes how closely the emitter and collector currents are in a common base circuit. DC alpha is designated as a alpha DC. This expression this is expressed in formula as alpha DC equals to IC divided by IE, collector current divided by the emitter current. So in most cases, the DC alpha is 0.99 or greater. The thinner and more lightly doped the base, the close alpha is to 1 or unity. So it means that the collector current and emitter current are almost equal. So it depends on how thinner the base is or how lightly it is. Number 4, a transistor has the following currents. IE is equals to 15 milliamperes. IB is 60 microamperes. Calculate alpha DC. Firstly, we need to calculate IC. So IC will be equals to IE minus IB. It gives us 14.98 milliamperes. Then alpha DC will be IC divided by IE. So here it gives us 0.996. Why? Because we have a very small IB value, which is 60 microamperes. The common emitter configuration. So here we have our emitter common to both voltage sources VPP, which is the voltage between the base and the collector. Then we have VCC, which is between your collector and emitter voltage. So here in this case, still IE would be equal to the base current plus the collector current. Common emitter configuration. So your emitter is common to both voltage sources. Then you'll have your input AC voltage on the base side, and then your load will be connected on the collector emitter side. The figure on the previous slide shows the common emitter configuration. VPP provides the forward biasing for the base emitter junction, and then VCC provides the reverse biasing for the for the collector base junction. It is called common emitter configuration because the emitter lead is common to both the input and the output sides of the circuit. DC beta, it's the current gain of a transistor. In the common emitter configuration, it is called DC beta. So DC beta is expressed in the formula as IC, which is your collector current, divided by your base current IB. Example 4, a transistor has the following currents. IC is equals to 10 milliamperes, IB is equals to 50 microamperes. Calculate beta DC. So beta DC will be IC divided by IB. So it gives us 200. It's a ratio 200. Example 5, a transistor has beta DC of 150 and IB is equals to 75 microamperes. Calculate IC. So IC would be equals to beta times IB. 150 times 75 microamperes. Then it gives you 11.25 milliamperes. What is the relationship between alpha DC and beta DC? If beta DC is known, alpha can be found using the formula alpha DC is equals to beta DC divided by 1 plus beta DC. Likewise, if alpha DC is known, beta can be found using the formula beta DC is equals to alpha DC divided by 1 minus alpha DC. Example 6. If beta DC is equals to 100, calculate alpha DC. Alpha will be equals to beta divided by 1 plus beta, giving you 0.99. Example 7. A transistor has alpha DC of 0.995. Calculate beta DC. So beta will be equals to alpha divided by 1 minus alpha, giving you 199. Okay, here we have a common emitter connection. A shows the circuit. So in this circuit, your emitter is common to both VPP and VCC. And then B shows the graph of IC versus VCE for different base current values. So you have whereby your base is equals to 0. So when your base is equals to 0, IC would be also be equals to 0, no matter what the value of VCE. So this one is called the cutoff region. Then we have, for example, here for IB equals to 10, between 0 and 1, an increase in VCE affects the value of IC. So it's increasing linearly. So this part here is called the saturation region. So the value of IC is not controlled by the value of IB. Then from 1, you notice that it's a straight line. Any increase in the value of VCE does not affect the value of IC. So this is called the active region. But you can increase the value of VCE up to the maximum value that the transistor can handle. So once you reach that maximum value, then it reaches your breakdown region. Then you can do the same for IB equals to 20, IB equals to 30. You have the saturation region. Once it reaches saturation, then it's the active region. So on the active region, the value of IC is not controlled by any changes in VCE. Okay, the circuit shown in A, VPB, it's the base supply voltage. So it is used to forward bias the base emitter junction. RB, it's the base resistor. It provides the desired value of the current IB, base current. VCC is a collector supply voltage. It provides the reverse biasing voltage required for the collector base junction of the transistor. Transistor voltages and currents. Assume VPP is varied to produce a base current of 50 microamperes if beta is equals to 100. So it means that IC would be equals to 100, which is your beta, multiplied by 50 microamperes, which is your base current. So it will give you an IC of 5 milliamperes. VPP can be adjusted to provide a wide range of IB and IC. As long as the collector base junction is reverse biased, when IB is equals to 50, IC will remain 5 milliamperes regardless of VCB. Also, VCC can be varied from a few tenths of voltage to several volts without the effect on IC, provided that VCB breakdown voltage rating of the transistor is not exceeded. When VCB is greater than 0, the collector base diode is reversed biased. Thus, the collector current IC is equals to beta multiplied by IB. This means that IC is slowly controlled by IB, not VCC. From the circuit diagram, note that VCE is equals to VCB plus VBE. Operating regions of a transistor circuit. The saturation region. From the graph, when VCE is 0, IC is 0 because the collector base junction is not reverse biased when VCE is equals to 0. Without a positive voltage at the collector, it cannot attract electrons from the base. When VCE increases from 0, IC increases linearly. The vertical portion of the curve near the origin is called the saturation region. The breakdown region. When the collector base voltage is too large, the collector base diode breaks down, causing a large undesirable collector current to flow. This is the breakdown region, and this area of operation should always be avoided. Breakdown region is not shown because it is assumed that it will not occur when the circuit is designed properly. The cutoff region. Notice the IB equals to 0 curve nearest to the horizontal axis of the graph. This is called the cutoff region because only a small collector current IC flows. A transistor is said to be cut off when its collector current IC is equals to 0. Active region. The active region of a transistor is where the transistor curves are nearly horizontal. When the transistor operates in the active region, the collector current IC greater than IB by a factor of beta. So in the active region, IC is always equals to beta times IB. In the active region, the collector circuit acts like a current source. So the first part here, it's the cutoff. So the cutoff is the one that's shown in red near the x-axis. This is when IB is equals to 0. Then we have the saturation region from 0 of your VCE. As VCE increases, IC also increases linearly. So this is called the saturation region. On the saturation region, the value of IC it's not controlled by IB. And then we have the active region. On the active region, the value of IC is controlled by the small amount of IB. IC is equals to beta times IB in the active region. And then we have the cutoff region that is not shown here. Cutoff region is when you reach the maximum value of VCE. So it's not shown here because we assume that it will not be reached if the circuit is designed correctly. Then we have the circuit in A here. We have a common emitter configuration. We have VPP supplying your base through a resistor RB. Then we have VCC supplying a collector to a resistor RC. VPP is the base supply voltage. It is used to forward bias the base emitter junction. Then RB, the base resistor, provides the desired value of current IB. VCC is the collector supply voltage. It provides the reverse biasing voltage required for the collector base junction of the transistor. RC provides the desired voltage in the collector circuit. Base bias with a single supply. So in the circuit below, solve for IB, base current, IC, collector current, and VCE, the voltage between the collector and the emitter. So here we have one single supply, meaning that your base and your collector are both connected to one supply. On the previous question, we had two supplies. We have VPP and VCC. VPP supplied the voltage for your base through resistor RB, and then we had VCC supplying the collector through RC. So now here we have one voltage supply. VCC is connected to both RB and RC. So here it means that you will have current IB that is flowing on resistor RB through VPE to ground, and then you will also have a current that's flowing through your collector, then between VCE to the emitter and ground. So it means that on this circuit, the two currents IB plus IC would be equal to the emitter current. So they want us to calculate IB, IC, and VCE. So IB will be equals to VCC minus VPE divided by RB. How did you get this? Total voltage is VCC. We have a voltage drop between your resistor RB, and then we also have another voltage drop across the base emitter. The voltage drop between the base emitter is 0.7, and then the voltage drop on your resistor RB is equals to IB times RB. We know the value of VCC, we know VPE, we know the value of the resistor, so we can calculate the unknown value, which is IB. This is how we calculated it. So IB is 79.44 microamperes. From there, we know that IB is equals to beta times I, or we know that IC is equals to beta times IB. This gives us 7.94 milliamperes. Then VCE. How do you get the formula for VCE? VCC is equals to the voltage drop on the resistor RC, and then we also have a voltage drop between your collector and the emitter, that's your VCE. So that resistor it's equals to IC times RC. We know the value of IC, we know the value of RC, so the only unknown is VCE. So VCC minus ICRC giving us 7.06. DC load line. The DC load line is a graph that allows determination of all the possible combinations of IC and VCE for a given amplifier. So for every value of IC, the corresponding value of VCE can be determined in the DC load line. So here we have our VCC or VCE on the horizontal, then on the vertical we have our IC. So here we can determine what is the saturation current, what is the cutoff voltage, and then also what is the Q point of this amplifier. The saturation current IC, this is the collector current IC when the transistor is saturated. VCE off, this is the collector emitter voltage when IC is equals to 0 for the cutoff condition. During the cutoff collector emitter region, it's seen as an open. At saturation, collector emitter region is treated like a short circuit since VCE is equals to 0 for the condition. Therefore, VCC will be equals to ICRC, and then IC saturation will be equals to VCC divided by RC. At saturation, further increases in IB produce no further increases in IC because VCE is equals to 0. Midpoint biasing. With no AC signal applied to the transistor, the quotient point values of IC and VCE exist at a specific point on the DC load line. Amplifiers are mostly biased so that the Q point is the center of the DC load line, so that ICQ is equals to half of the saturation current, and then VCEQ is equals to half of VCC. VCEQ presents the quotient collector emitter voltage. ICQ represents the quotient collector current. Centering the Q point on the DC load line allows the optimum AC operation of the amplifier. Example, figure 28 to 16 solves for IB, IC, and VCE. Also construct a DC load line showing the values of IC saturation, VCE cutoff, ICQ, and VCEQ. So this one here is also the base biasing with a single supply. In this circuit, VCC, if you look at it from the base side, VCC is equals to IBRP plus VPE. And then if you look at it from the collector side, VCC is equals to ICRC plus VCE. So we have unknowns here, which is the value of IB, the value of IC, and the value for VCE. So to calculate the value of IB, we will look at it from the emitters, from the base side. VCC equals to IBRP plus VPE. So the only unknown would be our IB, which would be equals to VCC minus VPE divided by RB. And then to calculate IC, we take beta times IB. And then to calculate VCE, VCE will be the VCC minus ICRC. So our IB will be VCC minus VPE divided by RB, giving us 28.97 microamperes. Then IC equals to beta times IB, that's 4.35 milliamperes. VCE will be VCC minus ICRC, giving us 5.48. And then IC at saturation, we calculate it using VCC divided by RC. Where do we get this formula? It's the same as this formula we used above for VCE. But remember, at saturation, VCE is equals to 0. So if VCE is equals to 0, what will be the value of IC? So you take the VCC to the other side, then divide it by RC. Then it gives you 8 milliamperes. And then VCE at cutoff, we take the same formula, but when at cutoff IC is equals to 0, so it means that our VCE will be equals to VCC. So this is how you will plot your DC load line. VCE at cutoff is equals to 12, and then IC saturation will be equals to 8. Then the Q point would be at the center here, which is the value of IC here, and then the value of VCE that you calculated. Example, design a base bias NPN transistor circuit with the following parameters: VCC equals to 18 volts, RC equals to 2.4 kilo ohms, and then beta DC equals to 150. Determine the values of RP that will produce an ICQ of 3.75 milliamperes and VCEQ of 9 volts. Draw and label the DC load line for the circuit showing all the points. What is the power dissipated by the transistor? So the value of RB will be equals to VCC minus VPE divided by IB. Where do we get the value of IB? IB is IC divided by beta. So IC is 3.75, beta is 150, so it means that IB will be 25 microamperes. Then we can calculate the value of RB as VCC minus VPE divided by IB. 18 minus 0.7 divided by 25 microamperes, giving us 692 kilo ohms. Then IC at saturation is equals to VCC divided by RC. That gives us 7.5 milliamperes. And then VCE off will be equals to VCC, 18 volts. Power dissipated would be equals to VCEQ times ICQ, 33.75 milliwatts. Then you draw your Q point, IC at saturation, VCE at cutoff, and the value of VCE and IC at the constant point. Instability of the base biasing. The base biasing technique provides a very unstable Q point because IC and VCE are greatly affected by the change in the beta value. So if the transistor is replaced with one having a significantly higher value of beta, then the Q point might shift to a point located near or either at the cutoff or saturation. Beta also varies with temperature. Therefore, any change in transistor temperature can cause the Q point to shift. Voltage divider biasing. This is the very popular way of biasing a transistor. The advantage lies in its stability. If designed properly, the circuit is practically not affected by changes in beta caused by either transistor replacement or change in temperature. An example of the voltage divider biasing. So here we have a voltage divider circuit. Why do we call it a voltage divider? Because your base, on the base you have two resistors R1 and R2, which will divide the total voltage VCC. So voltage VCC is divided between the two. So when you look at it from the base side, VCC is equals to R1 plus VR2. So you can calculate what is the base current, which is the base to ground. Base current would be equals to V resistor R2. So using the voltage divider, VB will be equals to R2 over R1 plus R2 times the total voltage VCC. So in this case, the voltage across resistor 2 is equals to 2.38 volts, which is our VB. So if the voltage between the base and ground is equal to 2.38, and we know that the voltage between the base and the emitter is 0.7. So what is the voltage on the emitter resistor VE? So VB is equals to VBE plus VE, meaning that VE will be equals to VB minus VBE. So the resistor RE will have a voltage of 1.68. And then the current through the resistor RE will be equals to VE divided by RE. So it will be 7 milliamperes. And then because beta is equals to 100, IE it's almost equals to IC, which is the 7 milliamperes. VC, which is from C to ground, would be equals to VCC minus ICRC. And then VCE will be equals to VCC minus ICRC plus ICRE. So it gives us 6.32 volts. IC at saturation, this is when VCE is equals to 0. So we will take the formula that has VCE and make it VCE 0. So VCC divided by RC plus RE will give you the IC at saturation. Then VCE is when the value of IC is equals to 0. So in this case, if IC is equals to 0, IE will also be equals to 0. So for VCE at cutoff will be equals to VCC. So IC at saturation here will be 15 divided by the value of RC 1 kilo ohm plus RE 240. So it's giving us 12.1 milliamperes, and then VC at cutoff will be equals to our VCC equals to 15 volts. Then you draw your DC load line showing the value of IC at saturation and ICQ, and then VCEQ and VCE at cutoff. VB is the voltage measured from the base lead to ground voltage drop across resistor 2. The voltage divider is made up of R1 and R2. Therefore, when using the formula, VB would be equals to R2 over R1 plus R2 times VCC. So this is the voltage divider formula. Then VE, your emitter voltage. VE is equals to the base voltage minus the base emitter voltage VBE, 0.7 volts. IE is equals to VE minus VE divided by RE. Then on the voltage divider, IC is almost equals to IE. Then we say VC is equals to VCC minus ICRC. VCE will be equals to VC minus VE, or it can be equals to VCC minus ICRC minus IERE. But because IC and IE are almost equal, then we can say VCC minus IC into RC plus RE. So on the voltage divider, we ignore the value of IB. So IC would almost equals to almost equals to IE. Using an NPN transistor, sketch the voltage divider biasing configuration with the following parameters. RB1 equals to 22 kilo ohms, RB2 equals to 10 kilo ohms, with one terminal of RB2 connected to ground. RC is equals to 1 kilo ohm, RE 1 kilo ohm, VCC plus 30 volts. From the circuit diagram, determine VB, VE, VC, VCE, IB, IE, and IC. Calculating the endpoints for the DC load line. When the transistor is saturated, VCE it's almost equals to 0 for the voltage divider. So IC at saturation will be equals to VCC divided by RC plus RE. And then VCE at cutoff will be equals to VCC. So this is your circuit diagram for a voltage divider biasing. VCC is equal to 24 volts. You have R1 and R2. So to calculate the value of VP, you'll use the voltage divider formula for R1 and R2. Then the voltage across R2 is your VB. And then VB is equal to the voltage VPE plus VE. So you'll calculate VE using VB minus VPE. And then when looking at it from the collector emitter side, it means that VCC will be equals to ICRC plus VCE plus IERE. But you know that IE is almost equals to IC. So VCC will be VCE plus ICR plus IC into RB plus RC plus RE. Okay, we have a similar circuit again, but here we are now using a PNP transistor. If you notice the arrow on your transistor, it's pointing in, meaning that from P to N. So it's a PNP transistor that's used in here. So for a PNP transistor, you notice that VCC is negative. Emitter biasing. So on emitter biasing, you will have a positive VCC, and then you'll also have a negative VEE connected on your circuit. So if both positive and negative power supplies are available, emitter biasing gives a solid Q point that varies very little with temperature variation and transistor replacement. Emitter supply voltage VEE forward biases the emitter base junction through the emitter resistor RE. So here, to calculate the emitter current IE, we use the formula VEE minus VPE divided by RE. Note that IB is ignored in this equation for calculating IE. A more accurate formula for IE is VEE minus VPE divided by RE plus RB divided by beta. Then to calculate VC, it will be equals to VCC minus ICRC. Okay, this is where we end it. We'll share more examples on the group, and then we'll do calculations for the different biasing techniques shown.